Hey guys, I'm Tanya.
I'm McLean.
I'm Gaurav.
And I'm Pratik.
So today you'll learn about rational functions, and before you start, there are 6 important things that you'll learn through this video. So the first is the definition and the characteristics of rational functions. You'll learn how to find the x and y intercepts. You'll learn how to determine the symmetry, find the asymptotes, find the holes, and finally sketch the graphs. You guys may be wondering what a rational function exactly is. I'm sure you have heard about rational numbers. A rational number is a number in the form of p over q, where q is not equal to 0. Similarly, a rational function has the form of p of x divided by q of x, where q and p are both polynomials. So typically, a rational function is defined as a polynomial divided by a polynomial, or simply a ratio of 2 polynomials. So here you can see in this example, x minus 3, which is a polynomial, is divided by x plus 7, which is also a polynomial. Alright guys, let's talk intercepts. I'm willing to bet that most of you have had to find the intercepts of a function before. You will find the x and the y intercepts in a rational function just as you would in a normal function. To find the x-intercepts, you would set the y equal to 0. That's exactly what we did in this example that we have on the screen. We set the entire equation equal to 0 and we got x equals to 3, which is x equals to 3 on the x-axis. Here we have a linear polynomial in the numerator. If you have a quadratic, you could factor or use the quadratic formula. If there's a degree of 3 or higher that isn't groupable, you would use synthetic substitution to find its zeros. Now, in order to find the y-intercept, you would simply substitute 0 in for x. So in our example here, we get f of 0 equals negative 3 over 7. So there you have your x and y-intercepts. Easy enough, right?
You all probably remember symmetry as one of the easiest parts of math in elementary school, right? Well, now we're in high school, and the teachers don't generally allow us to fold papers to test for it anymore. There are 2 types of symmetry: y-axis symmetry, also known as even symmetry, and origin symmetry, also known as odd symmetry. But how exactly do we find it? You could find the symmetry of a graph without even graphing it. For an equation to have odd symmetry, f of negative x must equal negative f of x. Let's consider this equation. F of x equals x over x squared minus 4. You would substitute negative x for x and negative f of x for f of x. Here we have odd symmetry. Now for the x-axis symmetry, let's consider the equation f of x is x squared minus 9 over x squared minus 4. For a function to have even symmetry, f of negative x should be equal to f of x. So for this equation, when we substitute negative x for x, we get the exact same equation as before. There you have even symmetry.
Alright, here comes the best part. Asymptotes, everyone's favorite word. An asymptote is simply a line that the graph of a function gets closer and closer to, but the two never actually touch or cross, much like the characters of a sad romance novel. There are a few different types of asymptotes, the first and most important of which are vertical asymptotes. Vertical asymptotes are, surprise, vertical, and can be found by setting the denominator of the function equal to 0. The resulting value or values cannot be values of x, because of that pesky divide by 0 error we hate so much. In this example, the denominator is factored to be x minus 3 times x minus 2. So, by setting each factor equal to 0, we get x equals 3 and x equals 2 as our vertical asymptotes, meaning the graph of the function will never cross over those lines. Remember, friends don't let friends divide by 0.
Where there's a vertical asymptote, there's obviously going to be a horizontal. Horizontal asymptotes are, yet another surprise, horizontal. Unfortunately, there are not one, but two situations where there would be horizontal asymptotes, so you need to learn two methods. If the degree of the numerator is the same as the degree of the denominator, then you would divide the leading coefficient of the numerator by the leading coefficient of the denominator. If you didn't already know, the leading coefficient of a polynomial is the coefficient of the term with the highest degree. For example, it would be 4 in 4x cubed minus 2x plus 5. The second method is to be used when the numerator degree is lower than the degree of the denominator. If you're confronted with this situation, good for you, because the horizontal asymptote will always be y equals 0. This is essentially the same as the first method, because 1 over x is pretty much the same thing as 0x plus 1 divided by x, and 0 over 1 is obviously 0. You may think that is it, that there are no more asymptotes. However, Alto 2 is mean. So the creators of math decided that horizontal asymptotes and vertical asymptotes weren't enough, and they had to add slant asymptotes. Obviously, these are diagonal asymptotes. And you're probably confused right now, but bear with me for a minute. So hopefully you guys remember synthetic division or just long division in general, because that'll come in handy. What you are going to do is you are going to divide through synthetic or long division the numerator by the denominator. Your result will be linear with a remainder at the end. We'll just get rid of the remainder for now, and we'll just graph that linear function. And that would be your slant asymptote for this function. If you guys know about asymptotes, let's talk about end behavior and the end behavior of asymptotes. So, in a normal graph, say you have y equals x squared. The end behavior would be what number y approaches as x approaches infinity, or negative infinity. So in this case, as x approaches infinity, f of x will also approach infinity, and if x approaches negative infinity, then f of x will still approach infinity. So now let's talk about the end behavior of asymptotes. We have to consider a couple different cases. First of all, you want to know what the end behavior is of a function with a horizontal asymptote. When you have a horizontal asymptote, the function will constantly go closer to the asymptote, however it will never touch it, or probably not touch it. Say we are looking at the end behavior of 2x minus 1 over x plus 2. Earlier in this video, we learned that to find the horizontal asymptote when the degrees of the functions are equal, we are dividing the leading coefficients. So here, we know that the asymptote will be at y equals 2. This means that as x approaches infinity, f of x will approach 2, because you're always going to approach that asymptote. That means that as x approaches negative infinity, f of x will still approach 2. This works with all horizontal asymptotes, whether the numerator has a lower or equal degree as the denominator.
Remember how earlier we mentioned that asymptotes were lines that could not be crossed? Well, unfortunately for all of us, rules are meant to be broken. This particular one, however, can only be broken in very special cases. To start off, you can only cross a horizontal or slant asymptote. You can never cross a vertical asymptote. To find the crossing point, you first need to find your asymptote. Say we are given the function shown. When you divide this out using long division, you find your remainder equal to be negative 23x minus 23. To find the crossing point of your asymptote, you would set this remainder equal to 0 and solve for x. If a solution exists, then there are as many crossing points as there are solutions. This scenario would leave you with x equals negative 1 to be your crossing point. So by now, this is a lot of stuff to know about graphs, and you figure they can't get any worse, right? Wrong. Here comes another crowd-pleasing topic. Holes. Relax, they're not donut holes. Depending on the function, a graph can have one or more holes, which are basically specific values of x and their resulting outputs, which are skipped over on the actual graph. Say you have a function like this one. Once you factor, you realize there's a common x minus 1 in both the numerator and the denominator, and you're all like, OMG, this makes my life so much easier, but of course, it's not that simple. Although you can simplify and graph the resulting function, first you'll have to set the quantity you cancelled out, in this case x minus 1, equal to 0. Once you get your answer, you have to find that x value on the graph and put an open circle where that value would normally be, which here is basically saying that the graph skips over x minus 1 and continues as it would otherwise. This is because if you go back to the original function and plug in 1 for x, you'll get a divide by 0 error, which isn't the greatest thing to have.
Alright, let's get real for a second. Graphing rational functions is a real pain in the asymptote, but with the few tricks you'll learn today, there is still hope. A general way to approach graphing a rational function is to first plot the y-intercept and corresponding x-intercept, which would be 1, 0 and 0, 1/3. Testing for symmetry is also beneficial. For example, if you know a function has y-axis symmetry, you'll only have to graph one half of the function and visually figure out the rest. You could initially graph the vertical and horizontal asymptote, which would be y is 1 and x is 3. It's a good idea to plot at least one point between and one point beyond each x-intercept and vertical asymptote. You could look for the crossing points of the horizontal asymptote, which would be at 2, 1. You could also write in the hole if there is one. Lastly, the end behavior could be used to continue the graph indefinitely. Sadly, we have reached the end behavior of our lesson. So this seems like a lot, right? Just remember that laziness is exactly like the number 8. If it lays down, it becomes infinite. After practicing, a lot of this will become second nature to you, so just study your notes and you'll do fine on the test. Keep in mind, numerator degree greater than denominator degree is a slant asymptote and or vertical. Numerator equal to denominator is a horizontal asymptote and or vertical. And numerator less than denominator would be an asymptote of y is 0 and or vertical asymptote. Good luck, guys.